Hello. In this section, we will solve some simple differential equations. In particular, the simple differential equations that we're going to look to solve are equations that we generated from using math models in the previous section. So let's just summarize that. The two differential equations that we generated were so this first one was the math model to represent a falling object. And the second one was a differential equation that represented population growth or decline for mice that are being eaten by owls. Okay, so we want to go through and solve these two differential equations. To do that, what we're going to do is we're going to start off with the second differential equation, go through and solve that one. Once we've done that, we're going to take the steps that we used, create a generalized formula for solving the differential equations that look like this, and then we'll use that generalized formula to solve the other differential equation to show that it works. Okay, so let's start off with this guy. Let's start off on a new page and see if we can go through and solve it. So the first thing I'm going to do is I'm going to go through and clean this up, manipulate it, make it look a little bit nicer. This 0.5, we're going to rewrite that as 1/2. We can go through and we can factor that out. Now at this point, what I'm going to do is I'm going to go through and I'm going to get these p's on the same side. The reason is if I get the p's on the same side, maybe I can go through and find something that I can do to get at just an underlying p function rather than have this derivative of p and p together. All right, so if we do that, we end up swinging this over. We get dp dt over p minus 900 equals 1/2. Now at this point, if you look at this, it looks a bit like an antiderivative of a natural log function, right? If you'll recall from previous calculus courses, getting ahead of myself there. If you'll recall, the antiderivative of dx over x is natural log x plus c. And you can see this looks a little bit like that in that we have a dp in the numerator and we have p minus 900. The minus 900 is just a u substitution off from just having x in the denominator. So what we can do is we can go through and we can integrate both sides with respect to t. The dt's over here will cancel on the left-hand side, and we'll end up with an integral that looks just like this, again, except it's got this minus 900, which is, again, is just a u substitution away from this formula. And so we can go through and we could say that the antiderivative here is the natural log of p minus 900. And then the antiderivative on this side would be 1/2 t. And now you'll notice I put a plus c here. So we get a plus c on the left and a plus c on the right, and we can just represent that with just a single plus c. Okay. And now at this point, we've got a an equation here where we have a single p. If we can go through and get that p by itself, then that will be the function that we could plug into the original differential equation that would make the equation true. So to unpeel this and get at the p, we can go through and we can make both sides the exponent of e. And then on this side, the e and the natural log cancel, and we get p minus 900. And over here on this side, we can rewrite this. This is e to the 1/2 t times e to the c. And now notice both on the right-hand side, these are both exponential functions, so they're both positive. That allows us to remove the absolute values. So we've got p minus 900 equals e to the 1/2 t times e to the c. And then next, what I'm going to do, which is maybe seems a little bit strange, I'm going to replace this e to the c with just a single c. Now, the reason that I can do this is that this c is going to end up being a constant value, and e to the c is a constant value. Just c itself is a constant value. And when we go through and solve for that c, it's going to adjust for the fact whether we have e to the c or c itself. I'll try and explain that better when we actually do an example. All right, so I'm just going to turn this into this instead. So this just is replaced with just a big C out front. And then I can move the 900 over. And what we have is we have a solution, a function, right? This is a function where if I plug in t values, right? Hold on, let's do this just to maybe make that clear. This is a function where I could plug in t values and it would go through and it would generate solutions. Okay, now if you take that function, now this is the way that differential equations work. If you take that function, that's the function that if you plug into the original differential equation, it will make the equation true. So solutions to differential equations are not numbers, they're functions. All right, it's the function that you would plug into the differential equation that would make it true. Okay, so with that in mind, let's just discuss this for a moment. Now you notice that we have the C here, right? So what this C here suggests is that there are multiple solutions to this differential equation that we could go through and we could plug in C values here and we could generate additional solutions. So let's explore that just for a moment on a separate page. Okay, so the C implies that there is more than one solution. This is going to be the norm. When we go through and solve differential equations, generally what's going to happen is we're going to get a C somewhere in the result, which will allow us to generate many solutions, infinite number of solutions to the differential equation. And if you go back and look at the solutions that we came up with, the direction field that we came up with last time, you'll see that we did end up with slopes, right, that where you could have fit multiple solutions onto those curves. So let's just take a quick look at that. Hold on, there we go. All right, so this is the direction field that we came up with last time. We've got a couple of solutions that are on there, but you can see that if you go through and take the points, you can slide them around and you can generate an infinite number of curves that fit onto the direction fields. Okay, so the direction field plot that we got last time does fit with the notion that we're going to end up with something where we can get multiple solutions. if we jump back, okay, so in order to go through and explore this further, one of the things that we can do is we can go through and we can plug in C values and generate solutions and just kind of play around with this. Just for example, we could go through and say, well, C could be 10, right? And we would get 10 e to the 1/2 t. C could be 25, and we would get 25 e to the 1/2 t. C could be, right, this is C equals 10, C equals 25. We could plug in C equals 0. If we plug in C equals 0, what would happen? Right, it's going to end up just getting rid of this term, and we would get P equals 900. You could have negative values for C. We could do C equals negative 10. We would get P equals 900 minus 10 e to the 1/2 t. So we can go through and generate solutions by plugging in C values. So let's just take a look and see what we get when we do that. And if you do that, so here is a picture that has a bunch of solutions drawn for various C values. So we have here C equals 25. That's this top one in red. C equals 10. That's the green one. C equals 0. That's the equilibrium solution one. And then we have minus 10 and minus 25. So we could see a bunch of solutions for different C values. And if we go through and compare those solutions with the direction field that we got, we can see that the two match up, which makes sense, right? So this is the direction field for this differential equation. This is the solutions, the actual solution curves to the differential equation for various C values, and the two should correspond, assuming that we've done it correctly. Okay. So the next thing that we want to look at is, how do we know which C value to use? So which curve is correct? Which of those various curves that we just drew with the different C values is the right solution? Okay, well, the only way that you're going to get a single solution to a differential equation is by having what's called an initial condition. So for example, in this case, we could go through and say something like the initial condition would be that we start with 875 mice. Okay, so once you have an initial condition, what you need to do is you need to go through and phrase it in terms of this function, right? In terms of the differential equation that we're trying to solve. And the way that you could go through and do that is that, notice that this function here, we've got p, right? And again, if I change it to be p of t, right? What this function does is that when we plug in a t value, it produces the population of mice at that time. So if we were to take this and translate it into this terminology, what we could say is p of 0 would equal 875. So the initial population, the population at time 0, would be 875. And once you've gone through and phrased it this way, what we can do is take this and combine it with this, and then we can solve for C. So let's go ahead and do that. Okay, so how do we do that? So what you want to do is you want to notice that we have P of 0 here. We've got P of t here, so we can plug in 0 for t, and you'll end up with 900 plus c times e to the 1/2 times 0, right? If we go through and simplify that, e to the 1/2 times 0 is going to be e to the 0, which is going to be 1. So we'll end up with 900 plus c. And then we know that p of 0 also equals 875. So we could just pop in 875 here, and we'll end up with 900 plus c equals 875. And then we'll end up with negative 25 equals c. And then if we take that and then plug that in, we end up with p of t equals 900 minus 25 e to the 1/2 t. Okay, so this solution here, right? The solution of this the function that we got here, that we generated here, this is going to be the solution that corresponds to an initial condition of 875 mice, right? So if you bounce back one more time to our graph, so you can see I've got a bunch of graphs here. In particular, the one that's going to match the initial condition that I set is going to be this one, the blue one, the one that's 900 minus 25 e to the 0.5 x, right? So use x instead of t. If we'd gone through and picked a different initial condition, we could have generated these other curves. So this initial condition here would have corresponded to where we have negative 10, that would have corresponded to 890 initial mice. The 900 here would have corresponded to 900 mice. This is 910 mice, 925 mice. You can actually see here, if you look closely, this point here is at 875. So that's 875 initial mice, 890, 900, 910, 925. Okay, and so all these curves represent the different solutions that you'd get for different initial conditions, and the one that we just went through and solved for is this bottom one. Okay, so the next thing we're going to do is we could go through and follow this exact same process to solve the other math model that we created. However, instead, what we're going to do is we're going to go through and we're going to generalize this result that we just created. And then once we create a general formula for solving differential equations that have the format that this last population problem had, then we can go through and see it and try and use that general formula to solve the other differential equation. Okay, so to do that, we're going to start off and say, let's create a differential equation that could represent a general version of what we just solved, right? So instead of dp dt, we'll use dy dt. And so we had 0.5 p, we're going to put ay, and then we had minus 450, and we'll just put minus b. Okay, so if you recall from what we just did, first thing that we did is we factored out the a. We could do a times y minus b over a. Then we went through and divided the y minus b over a to the other side. So we got dy dt over y minus b over a equals a. Then we integrated both sides. with respect to t. And then we said we could go through and use the antiderivative formula from natural log to generate the fact that this is going to be the natural log of y minus b over a. And then here we get at. Then we have our plus c, right? So we got a plus c from this side and a plus c from this side. We just put a single plus c over here. And then if we go through and have the natural log of y minus b over a here equals at plus c, we want to get at the y. We can do that by making both sides the exponent of e. Then the e and the natural log will cancel. And we'll get y minus b over a equals e to the at times e to the c. And then we can replace e to the c with just a single c. And then this is positive, so we can ditch the absolute value. Well, this is positive, so we can ditch the absolute values. And then we'll get y equals b over a plus c e to the at. So assuming we start off with this differential equation, we can get to here. We can actually take this a step further if we have an initial condition. We know that the initial condition, for example, y of 0 equals y naught. Then you can go through and you can actually take this a step further and solve for the c. Right? We'll have y of 0 equals b over a plus c times e to the a times 0. So we have y of 0 equals b over a plus c. And then if y of 0 is y naught, we'll get y naught minus b over a equals c. And then you can take that and plug it in. And we'll get y equals b over a plus y naught minus b over a e to the at. And that gives us a formula, a generalized formula that we can use to solve any differential equation that has this format with this initial condition. So let's go through and try that on our other equation. Okay, let's just leave this down here in the bottom right-hand corner and erase what's over here. Okay, so we had our other differential equation was dv dt equals 9.8 minus 1/5 v. All right, so we could go through and solve this using our generalized formula that I just erased up here. But instead, let's try and use the formula in its entirety by going through and setting an initial condition. So we want to set an initial condition. We want to go through and say that v of 0 equals something. Now, if you recall from the last lecture, if you go back and watch the last lecture, we got that the equilibrium solution was 49 meters per second. So we can go through and just say v of 0 is 47. And if we have all this information, then it's just a matter of making it fit the format, right? And the initial format for this was dy dt equals ay minus b. If you can make it fit this format, you can just jump right to the solution. Okay, so let's see if we could do that. So we've got dv dt. Now you notice that we have the variable that matches with the variable from the differential equation, or from the derivative. You want to have that first, so we want to rewrite this as negative 1/5 v plus 9.8. And then at this point, the only thing left is that we got a plus there. There's a minus in the formula, so you could do dv dt equals negative 1/5 v minus negative 9.8. And now we have everything we need. All right, this is going to be A, this is going to be B, this is V naught, right? Not Y naught, but V naught. And then just take all of those and just pop them into the formula. And we're going to get V equals B, which is negative 9.8, divided by A, which is negative 1/5, plus V naught, which is 47, minus this result here, times e to the A, which is negative 1/5 t. And if you simplify this, negative 9.8 over negative 1/5, we're going to end up with 49 plus 47 minus 49, e to the negative 1/5 t. And this simplifies to 49 minus 2 e to the negative 1/5 t. And now we can go through and look back at the direction field that we got last time and graph this and kind of see how the two compare. So basically just do the same thing that we did earlier. So this is the direction field that we got last time for 9.8 minus 1/5 y, or 1/5 v. All right, as we got slopes that looked like this. We went through and graphed a couple of potential solutions on there, and we said the solutions should look something like that. And you can actually even see the values on here, right? So this is an initial condition where we have the initial velocity is 54. This is the initial condition where the initial velocity is 47. So that's the one that we just went through and generated. So if we go through and graph what we just got, it should look like this. And if you go through into Desmos and graph 49 minus 2 e to the negative 1/5 x, or t, you end up getting a curve that looks just like that. So the result that we got by going through and solving the differential equation by hand does match with the result that we got with the direction field. Okay, so that is going to conclude this lecture on going through and solving some simple differential equations. So we went through and solved the population problem. Then we used that solution to generate a general solution. And then with that general solution, we went through and solved the other equation. Okay, so one comment before I conclude this, and that is, so you'll notice that we have a starting, form for the differential equation, and we have a finished solution for the differential equation. So this is going to be common throughout the course, where we're going to have a form for the differential equation and then like a solution formula, right, that we can go through and just jump from one to the other. So what you want to do is you want to memorize these, write them down, become accustomed to them. The idea is not that every time you'll go through and move this over and move this over and integrate both sides and so on and so forth. The idea is that you're going to see this format, and then you're going to have the formula either memorized or written down, and then you'll just jump right to the solution. All right, so that's going to be consistent throughout the course, where we're going to go from one differential form to another. And each time we'll have a method for going through and solving it, and that method frequently will just be a formula. Okay. All right, with that, thank you for watching, and I'll see you next time.